Hello. Today I'll be going over what a breadth-first search is and how we can apply it to this problem on Leetcode 785 is graph bipartite. So the breadth-first search is a very important search algorithm that's needed for graph traversal. Essentially what you're doing is you take a node, you look at its neighbors, you add them into a queue, and then you traverse the neighbors, and then so on and so on and so on. And you keep traversing their neighbors until you can't find any more neighbors. So for this problem, I'm going to go through a high-level overview of how breadth-first search factors into this. So first of all, the problem, as you can see here, they give us an example, 0, 1, 3, 2. So they give us a graph, and basically we want to see if we can divide the vertices into two groups. So for example, this one could be divided into 0, 2, and 1, 3, such that all the vertices in a group like 0, 2 are connected to only other vertices in the other group. So how I choose to imagine this problem is, as it's sort of similar to another problem known as the two-color problem. So imagine 0 is blue. So then in that case, the two edges that it has here to 1 and to 3, these two nodes would be red, in which case 2 has to be blue. So in this example, you can see number 2, you can see this is not bipartite, because if you have 0 as blue and 1 and 3 and 2 as red, then there's a contradiction here, because once you go to 3 and you look at 2, they need to be opposite colors, which is not possible here. So basically, if we can find whether or not we can two-color the entire graph, we can also find if it's bipartite. So let's go into the actual problem here. So I start off by initializing a set called discovered, and then I'll go through all the nodes from 0 to the length of the graph, and this is again because the node is recognized by its index in graph, and that's why we're going through it in this manner. Also, we go through all the nodes because if we do run a breadth-first traversal from one of the nodes and we don't reach all of the other nodes, well, then we still have to continue through all of the nodes to see if we can find another separate tree. So like if we have a forest, for example, where there are multiple disconnected sections. So first of all, we check if it's not undiscovered, and for the first node, it will definitely not be undiscovered. And we set the value of this node in the dictionary to 0, which I've commented here as blue. This is arbitrarily selected. It could be red. It doesn't really matter at all. So basically, we add this node to the queue right here, and then we iterate through the queue, and this is where we have our breadth-first search. So basically, we can see I implemented BFS with a queue. So while you have items in the queue, you are going to take the first item in the queue. So that was the earliest item that was added, and then you're going to go through all of its neighbors. So if one of its neighbors is already in discovered and the colors are the same, so let's say, for example, you had 0 equals 0, then that means your graph is not two colorable, because it means you saw it before and it had to have been the previous color, but now it's also touching this color, which is a contradiction. In that case, you return false. Otherwise, if the neighbor is not in discovered, which means we haven't ever seen it yet, then we'll set the color to the opposite color of the current node, so the node that we popped here at the top. So for example, if we had blue coming in, then all of its neighbors that were not undiscovered would be put in as red. And then we'll add it to the queue so we can traverse it later since it wasn't discovered. And note that the case that isn't covered here is if they are opposite colors. And if they're opposite colors, that means the algorithm is working as intended, and we don't want to append it to the queue because that would mean we're rediscovering stuff that we've already discovered. So basically, you'll iterate through for this specific component, and if there's more, this loop will cover it. And then at the very end, if through all of that it never returned false here, then that means that the algorithm must have proved that the graph is too colorable, in which case it will return true. So you can see the power of BFS here is its ability to traverse graphs relatively fast, and also in such a manner that you can use it in problems like this. What's key about BFS is that you can separate it out into levels. Every single level has its own distinction in this problem, which is very important. So like with other search algorithms such as DFS, it's not necessarily going to move outwards. Like I imagine it as radially outwards from a node. It might just go randomly based on whatever is arbitrarily at the top. Whereas BFS, it operates in levels, and so you can usually use this to path find, to find the quickest way. For example, if you have edges that aren't weighted, and you can also use BFS just really for any graph traversal, just to find something. So if you ever need to find something in a more complex algorithm, you can just run this simpler algorithm of BFS within it to try and find the path. And as you can see, the power of BFS is very, very large, and you can apply it to many diverse problems such as this one. In fact, you might not even think to use BFS in this one. But again, very strong algorithm to know.